Hey, guys,
Yeah.
you know what I could really go for right now?
What's that?
What?
Some Darude Sandstorm.
Oh,
Yeah, me
that'd
too.
be
I really like
tight.
that.
Oh,
But the computer's all the way over there.
Yeah, how
Oh,
are we gonna
crap.
how are we gonna
How will we ever turn it on?
Oh man.
it's so far away.
I
Um,
need my Darude.
Here's how it works. When you connect the battery to the rails, it will accelerate the rod into the battery.
When the battery is connected, it short circuits and creates a high current. We will consider our rails to be of infinite length because, compared to the distance between them, they are very long. Ampere's law tells us that the magnetic field produced by an infinitely long current-carrying rail is equal to mu naught times I over 2 pi r. Due to the positioning of the rod between the rails, instead of having two infinitely long rails, we actually have two half-infinitely long rails. Because of that, the equation for the field between them is the same as the equation for the field produced by one infinitely long rail. Using the Lorentz force law, we can determine the force being applied on the rod as it moves down the rails. Substituting in the equation for the magnetic field found before, we end up with this integral. We would like to find the force on the portion of the rod between the rails. To do this, we set our limits of integration to r and d plus r. After evaluating the integral, we arrive at the expression for the force being applied to the rod as it moves along the rails.
And that will knock down this tennis ball into the leaf blower.
So, this section of the calculations is for the pendulum with the tennis ball on it that gets knocked over by a battery that then goes to turn on the leaf blower. The tennis ball weighs 0.074 kilograms, and the length of the line is 2.14 blah blah meters. And so it swings down to a height of 0.22 meters when it hits the lever that turns on the leaf blower. So we have the period of the swing calculated here. You know, it's just the period formula with the length inserted into it. So we know the period is 2.94 seconds based on that calculation. Calculating the velocity out of it, so using mgh and 1/2 mv squared plus mgh at the bottom, we can calculate a velocity of 2.994 meters per second when it hits the lever. I calculated the centripetal acceleration, which is v squared over r. So I just plugged in 0.994 for v and 2.1463, which is the length of the line, in order to get the centripetal acceleration, which is 4.175 meters per second squared. Then calculated the force acting on the ball. That is not only the force of the weight of the ball, but also the centripetal acceleration times the mass of the ball when multiplied and added, gave a force of 1.03 newtons.
The leaf blower, which will power this sailboat longboard contraption. It will roll into the corner of this table, which will disrupt the balance of this weight system, dropping it onto the skateboard. It will then catapult into the shovel.
The purpose of this component was to find the initial acceleration of the tennis ball on the skateboard. After the bowling ball lands on the other side, the skateboard acts as a seesaw of sorts. That said, we can use the summation of torques equation to find the force and thus the acceleration on on the tennis ball. So if we state the equation of the summation of torque, we can separate that into just stating that the summation of torque on the left side is equal to the summation of torque on the right side. That means the torque on the tennis ball plus the torque on the center of mass equals the torque on the bowling ball. And then rearranging that, we can find acceleration. We have all of our given values by determining the mass and the distance away from the pivot point all of the components are. Plugging all of these into the rearranged equation above, we get that the initial acceleration of the tennis ball is 37.6 meters per second squared. So the purpose of this component is to find the velocity of the skateboard and bowling ball just after the bowling ball has hit. So using kinematics, we can find the final velocity of the bowling ball just before it's hit the skateboard. So yeah, using kinematics, we use the equation Vf squared equals Vo squared plus 2AD. And this gives us that the bowling ball is traveling at 12.5 meters per second as it lands on the skateboard. And since this is an inelastic equation, we are able to use this to find the velocity of both the bowling ball and the skateboard. So plugging in the values and rearranging the equation to find the final velocity, we get that this is equal to 9.04 meters per second.
That shovel will start to spin, and that in turn will disrupt these blue balls. Now, the blue ball up here will fall into this mallet, clicking the mouse.
This part is where the blue golf ball falls from its perch onto the mallet that then clicks the mouse. So as you can see, the golf ball weighs 0.04593 kilograms, and then it falls 3 inches. So I calculated the total energy, which was just mgh, which was the distance between where the golf ball was being held on the clamp down to the mallet. So it just made a simple fall so it could be calculated through the potential energy, which ended up being a total energy of 0.034 joules. And then to calculate the velocity, I used Ke equals mgh, which I calculated here to get a velocity of 1.22 meters per second.
Wow!
And that will turn the lawnmower on. Okay, it's a leaf blower. I've been informed it is not a lawnmower.